Okay, folks, how we doing? I'm recording here this last lecture for our Chapter 3 section. So what I have in front of me here right now are all the learning goals that I've gone through in the previous lectures, all right? Um, excuse me. So as always, make sure that you're making good progress towards these learning goals, okay? So this is the only ones we have left for this chapter, which I'm going to talk about in this lecture, and that is number 6. Understand the concept of limiting reactant or limiting reagent, we also call it that, as well as stoichiometry calculations. Understand the difference between empirical formula and molecular formula, and be able to calculate mass percent of an element given its chemical formula. So I'm going to go through these 3 things, and this is going to be largely more example problems because I really like teaching through examples, okay? So let's talk about the limiting reagent. And to set up the limiting reagent discussion, let's pretend we're making ham and cheese sandwiches, okay? And let's suppose we've got like Gordon Ramsay tells us to create the perfect ham and cheese sandwich, we need exactly 3 pieces of ham, 1 piece of cheese, and 1 bun, okay? And this is what we call our perfect stoichiometric proportions, okay? One sandwich has a ratio of 3 pieces of ham to 1 piece of cheese to 1 bun, all right? So suppose now I've got 4 pieces of ham and 2 pieces of cheese and 2 buns, okay? How many ham and cheese sandwiches could I make? And now I know what you're thinking. Well, why not just have, 2 pieces of ham and 1 piece of cheese per bun and you'd be good to go. But remember, Gordon Ramsay told us we have to have exactly 3 pieces of ham and 1 piece of cheese. And so if we think about this in terms of chemistry here, we don't have enough materials to make exactly 2 sandwiches. We only have enough materials to make 1 sandwich. We're short 1 piece of ham, and instead of sending that piece of ham off, we're not going to embarrass the kitchen, right? And we're just going to say, nope, we only have enough to make 1 of those sandwiches. And then, of course, if I only had 3 pieces of ham and no cheese at all and just 1 bun, then I can't make any sandwiches. I could just make a ham sandwich, but I can't make this ham and cheese sandwich according to my perfect stoichiometric proportions. So when we talk about this idea of the limiting reagent, think back to this example. It's going to be no different than this example, okay? So let's test it out. So how many sandwiches can we make if we have 12 slices of cheese and 15 slices of ham and 6 buns, okay? Well, we know from this previous slide that we have this perfect stoichiometric proportion. We have a recipe or a ratio, right? We have 3 hams and 1 cheese and 1 bun. And that makes 1 ham and cheese sandwich, okay? So that's our chemical reaction, right? We could think of 3H plus 1C plus 1B makes 1 HCS, 1 ham cheese sandwich, okay? So now when I go and I've got all of these materials, so what can I do? Well, let's see how many sandwiches we can make from the ham, right? So we know we have 15 hams, okay? And my perfect stoichiometric proportions told me I needed 3 hams per 1 ham cheese sandwich, right? So the ham and the ham cancels, and what I'm left with is I could make up to 5 ham and cheese sandwiches just based on the ham, right? Well, what about the cheese? Well, I know I've got 12 slices of cheese, and my recipe told me that I only need 1 piece of cheese to make 1 ham cheese sandwich, so that means from the cheese I could make 12 ham and cheese sandwiches, right? And similarly from these buns, right, if I know I have 6 buns and I know I only need 1 bun to make 1 ham and cheese sandwich, that means that I could make 6 ham cheese sandwiches. So now how many complete ham and cheese sandwiches could I make? And the answer is 5, okay? Because the least is the most? I know that makes no sense, but I want you to think about that in terms of limiting reagents, right? The least number of reagents results in the most number of reactions that can go, okay? Or in this ham and cheese sandwich example, the least number of ingredients gives me the most ham and cheese sandwiches that I could make, all right? So let's test this out with an actual chemical reaction, okay? And this is, again, another one of these kind of big word problems that I like to do. So I'm going to show you how I break down this problem, how we turn the problem into a reaction, and how we go about doing this. Okay, so let's read it. So nitrogen gas, okay, so first I'm going to underscore that, and I'm going to remind myself nitrogen gas is N2, right? Can be prepared. So can be prepared means nitrogen gas is going to be a product, okay? Nitrogen gas can be prepared. Automatically, that tells me I am making nitrogen gas. Bypassing gaseous ammonia over solid copper 2 oxide at high temperature. The other products of the reaction are solid copper and water vapor. Okay? So that tells me my other products, right, are solid copper. So I'll write a Cu solid. We know that this is nitrogen gas, so I got to put that G down there for gas. Let me go ahead and make this just a little bit more clear. Okay. And they also tell us the other products are solid copper and water vapor. So I know water vapor is H2O gas. Okay, there's my products. What about my reactants? Well, it said gaseous ammonia, NH3. Okay, great. And solid copper 2 oxide. Okay, copper 2 oxide is CuO. Because remember, each oxygen's -2, and if the copper, that copper 2, remember, tells me that that's a +2 copper. Okay, so I need 1 copper for every oxygen. And then now, of course, I have to balance this equation because I can see that I've got 2 nitrogens here, but only 1 nitrogen there. So I'm going to put a 2 in front of there to start. All right. And let's see, when I do that, that gives me 2 times 3. That gives me 6 hydrogens. Okay. And here I only got 2, so I'm going to put a 3 over here. And now my hydrogens are balanced, so that's good. But now I've added 3 more oxygens, but I only have 1 oxygen on this side. So now I'm going to add 3 to this side. And then finally, I see now I've added 3 coppers, so now I need 3 coppers over here. And this is finally balanced. Okay, let's double check. 2 nitrogens, 1, 2, and then 2 nitrogens. And then 2 times 3 gives me 6 hydrogens. And 3 times 2 gives me 6 hydrogens. And then 3 oxygens, 3 oxygens, 3 coppers, 3 coppers, we're good to go. Okay. So now, what is this problem even asking me? It says, if a sample containing 18.1 grams of ammonia, NH3, and I'm going to write 18.1 grams right there under the ammonia, is reacted with 90.4 grams of copper 2 oxide, what is the limiting reagent? Okay. And how many grams of N2 will be formed? So I'm going to put a question mark right there for how many grams. And I'm just going to back up really quick. I think I realized I forgot to say, because in a simple example we were doing, the ham is my limiting reagent. Because, so I'm sorry, I forgot to say that in the previous slide. The ham is limiting because you notice from the cheese, I could make 12 sandwiches. From the buns, I could make 6 sandwiches. But from the ham, I could only make 5 sandwiches. So I would run out of ham first. That's what makes this the limiting reagent. Okay? So now in this chemical reaction, okay, and granted, you know, I gave you a pretty hard problem to work through, but let's just focus on that. Now we have a reaction. Okay, we have 18.1 grams of ammonia and 90.4 grams of copper 2 oxide. Which one is limiting? Okay, the ammonia or the copper. And once we know which one is limiting, how much nitrogen can we even make? Okay. So what we're going to do, we're going to do two calculations. We're first going to start with this 18.1 grams of ammonia and come all the way over to nitrogen. And we'll see how many grams of N2 can be formed by 18.1 grams of NH3. Okay, so I'll call that number 1. Then we're going to do a second calculation that I'll call number 2, where we're going to see how many grams of nitrogen can be made from 90.4 grams of copper 2 oxide. And the least is the most amount of nitrogen we can make. And whichever one turns out to be the least, whichever one makes the least amount of nitrogen, was the limiting reagent. Okay, so let's start on this calculation number 1. And like always, I'm going to start with the number that I have, which is 18.1 grams of NH3. Okay, and so what I need to do, I need to convert 18.1 grams of NH3 into moles of NH3, and then I can convert moles of NH3 into moles of N2 from this 2-to-1 ratio. And then finally, I can convert moles of N2 into grams of N2. Okay, so here I need to cancel my grams of NH3 and make it moles of NH3. And I do that with the molar mass. Okay, and so if you look up the mass of nitrogen and hydrogen and do all that, you should get 17.02 grams of NH3 in 1 mole. Great, so I can cancel those. And now I need to convert moles of NH3 into moles of N2, just like I did back here, right? Where I said, I know that in my perfect ratio, 3 slices of ham makes 1 ham and cheese sandwich. So that's my conversion factor from one reagent to another reagent, or from one reagent to, in this case, a product. Okay. So my reaction, let's write these a little bit more clear. That says mole, mole. Okay. Mole. Okay, so I know from this balanced reaction, I have 2 moles of NH3, right, for every 1 mole of N2. Remember, there's no coefficient there, so we just assume that it's 1, okay? And then now finally, look, I reminded myself that I needed to get to grams of nitrogen, so finally I can say moles of nitrogen to grams of nitrogen. And I know from the periodic table, in 1 mole of nitrogen, there's 28.00 grams of nitrogen, because each nitrogen atom is 14 grams per mole. So 2 of them makes 28. Okay. And now let's see how we did on the canceling. Mole of NH3 cancels with mole of NH3. And look, I'm not canceling the number. I'm just canceling the unit. Okay. And then mole of N2 cancels with mole of N2. And then what I'm left with in this answer will be some grams of N2. Okay, so let's do the numbers. So I'm going to say 18.1 times 1 times 1 times 28. So I could probably just make that 18.1 times 28, 0.00, sure, equals 506.8 something, something, something. And then I've got to divide it by 17.02. So we'll say divide by 17.02 equals, and then I've got to divide it by 2. Divide by 2. And I can still say, divide by 1 again, but we know what the result of that will be. So 14.888, and you can see I've got from the 18.1, 3 sig figs, so this should be 14.9. Okay. So 14 grams of nitrogen can be made from 18.1 grams of ammonia, assuming that I had a large excess of copper 2 oxide. And what that means is, by assuming I had a large excess of copper 2 oxide, that in this calculation, Copper didn't even enter the equation, right? So we're just assuming copper is in excess, like we have as much copper 2 oxide as we need. Now we're going to have to flip the script on that and calculate it the other way. We're going to calculate it starting with the 90.4 grams of copper 2 oxide, assuming the NH3 is in excess, and we'll see how much nitrogen we make from there. Okay. So I can follow this same kind of pattern where I know I'm going to have to convert grams of copper 2 oxide into moles of copper 2 oxide, and we know from the periodic table that there's 79.55 grams per copper oxide per mole. So prove this to yourself. Prove that you can get that molar mass, okay? And then I know the grams and the grams are going to cancel. And then now following the same pattern that I did, I know I want to convert moles of copper 2 oxide into moles of nitrogen. And my balanced recipe says 3 moles of copper 2 oxide are needed to make 1 mole of nitrogen gas. And then finally I can copy the line identically by saying I know 1 mole of nitrogen is 28.00 grams of nitrogen, and then all of my units are going to cancel, and then similarly I'm left with grams of N2. That's going to be the unit of my final answer. So let's do the calculation. I'm going to do 90.4 times 28. Okay. Equals. And now I'm going to say divided by 79.55. Equals. And now I'm going to say divided by 3. Equals. Okay, 10.6 grams. 10.6 with 3 sig figs. Okay, so now let's compare those two, all right? If I started with 18.1 grams of ammonia, and I wasn't concerned with how much copper 2 oxide I had. I was only thinking about what I could make with my 18.1 grams of ammonia. I can make 14.9 grams of nitrogen with that amount. But now if I ignore the ammonia and I look at the copper 2 oxide instead, 90.4 grams of copper 2 oxide will only make 10.6 grams of nitrogen. And remember, the least is the most. So how many grams of N2 can be formed? That many. And which is the limiting reagent? Copper 2 oxide is limiting. And so what does that mean to be limiting? Well, it means you're going to run out first, okay? It means that we're going to use up all of the copper 2 oxide. And when we think about a chemical reaction, we can't just think of like one reactant at a time, right? Both reactants are reacting. So when I take this 90.4 grams of copper 2 oxide and 18.1 grams of ammonia, the copper 2 oxide is going to run out first. And thereby I'm going to have excess NH3. So this will be my, let me put this in a different color so we can later on go back and look. Sure, that gold color looks nice. Oh, what do you want to bet it's not going to show up very well? Actually, not bad. Excess and then limiting, okay? And then, oh yeah, I gotta move the talking head out of the way to switch back colors. Okay. Here you go. All right. So we could even go as far as to calculate how much excess ammonia we would have. Okay. And we are going to do that next. Okay. So here's another problem. Oh, my arrow. What happened to my arrow? Let's draw that in right there. Okay, beautiful. All right, so ammonia is produced from the reaction of nitrogen and hydrogen according to the following balanced equation. Okay, so this one was a little bit nicer because there's already a balanced equation. And just kind of confirming really quick, I see 2 nitrogens on this side and 2 nitrogens on this side and 6 hydrogens on this side And 2 times 3, 6 hydrogens on that side. Beautiful. Okay, so now the problem is asking me, what is the maximum mass of ammonia that can be produced from a mixture of 1.00 times 10 to the 3 grams of nitrogen, that's 1,000, and 5.00 times 10 to the 2 grams of hydrogen, that's 500. And so remember, I'm going to do one problem. We'll call the hydrogen number 1, where I try to figure out how much mass that's going to create. And then I'm going to do a second calculation, number 2, where I figure out how much ammonia I can make from that amount of nitrogen gas. Okay? Hopefully I left myself enough room. It looks like I did not. So let's go for it. Okay, so let's do number 1. I'm going to try to write a little bit smaller than I normally do. So I'm starting with the first number that I have. You know, that's why I draw this arrow, right? This arrow helps me visualize the calculation I need to do. I'm going to start with this number, and it's going to spit out that number. Okay, so I can say 5.00 times 10 to the 2 grams of H2. And grams of H2, I need to convert that into moles of H2 because mole is how I compare things in a chemical reaction. And let's see here. The periodic table tells me it's 2.016 grams of hydrogen in 1 mole. Okay. So from this balanced reaction, it tells me 3 moles of hydrogen make 2 moles of ammonia. All right. So we'll say 3 moles of H2 makes 2 moles of NH3. And don't forget to cancel out those units as you are going. At least that's what I like to do. It helps me check that I'm on the right path. And then now finally I'm at moles of NH3, but I need to be at grams of NH3, right? So I know I can say mole NH3 per gram NH3. And from that last problem, right, we calculated that it was 17.02 grams of NH3. Okay, so let's do that calculation. So 500 times 10 to the 2, I can enter in this calculator by saying 500 E2, oops, not that way. I go 5.00 E2, and look, it tells me 500, okay? That's what it's supposed to be. So 500 times 1 times 2 times 17.02. So 500 times 1 is 500, times 2 is 1,000, times 17.02 is this number, and then divide by 2.016 equals, and then divide by 3 equals. And I get, yes, so the way this calculator works, that's 2,814, okay? And with, so I want to write all that down, 2,814, and I want to do only 3 sig figs. So this is where I'm going to use scientific notation, and I'm going to say 1, 2, 3, okay? So that's 2.81, but I'm not going to write 814. I'm just going to write 2.81 because that gives me my 3 significant digits times 10 to the 3rd power. Okay, and that's grams of NH3. Okay, so now let's do number 2. Let's calculate it for, so we started with the hydrogen, now let's start with the nitrogen. Okay, so now we're going to say 1.00 times 10 to the 3 grams of nitrogen. And I know I need to go moles of nitrogen. Oops. Nope, I don't need to do that. I need to stick with the same unit, right? If I have grams of nitrogen up top, I need to have grams of nitrogen on the bottom. Then moles of nitrogen on the top. And I know from my table that it's 28.00 grams of nitrogen and 1 mole of nitrogen. And then now I'm at moles of nitrogen, and I can see in my balanced reaction 1 mole of nitrogen makes 2 moles of ammonia. So mole of nitrogen, it's a mole of ammonia. 2 moles of nitrogen makes 1 mole of ammonia. And then finally, this very last line I can copy identically from above because it's the same conversion, moles of nitrogen to grams of nitrogen. Okay, and my units cancel all very nicely. And so let's calculate this out. Okay, so I can write 1,000 on this calculator by saying 1 point, I'll just put the zeros in just to be complete, 1.00 e to the 3, and I'm just going to say equals, yep, that's 1,000, times 1 times 1 times 17.02. So times 17.02 equals, and then now divide by 28.000, right? And then divide by 2. And I get a number that I did not get in my notes. Oh, you know why? I know what I did wrong. Haha, those of you that are watching are probably like screaming at your computer screen like, no, no, no. 1 mole of nitrogen makes 2 moles of NH3. Geez, Harmon. Okay, let's make sure that everything else looks good. Okay, now let's try it. So we know 1 times 10 to the 3 is 1,000 times 2 times 17.02 equals, okay, and then now divide by 28. Divide by 28.00. Okay, that's the number I have in my notes. And so, okay, I'm going to write that down as 1,216. I'll round it up to 216. But I still need 3 sig figs out of this. And so right here's where my comma is. So that's going to go 1, 2, 3. Okay, we'll make that like a very clear comma. So now that's 1.2 something times 10 to the 3. And for 3 sig figs, it's 1.2. And then that 6 is going to make that 1 round up to another 2. Okay, grams of NH3. So what is the maximum amount that can be created? Remember, the least is the most. So 1.22 times 10 to the 3, that's 1,220, or 1,216 with 4 sig figs grams of ammonia. Okay. Now it says what mass of which starting material would remain unreacted. So what that means is which one is in excess? Which one do I have leftovers from? Okay? And so it's going to be the hydrogen. And the way that I know it's got to be the hydrogen is because, look, the hydrogen could possibly make a lot more ammonia than the nitrogen did. So that means nitrogen is limiting. I'm just going to write this down for my own clarity. And hydrogen is in excess. So that's what we're going to have leftovers of, hydrogen. Okay. So how do I calculate which starting material remain unreacted? Okay, this is a little tricky. So what we need to do is actually work backwards. We're going to start with this number, 1.22 times 10 to the 3 grams of NH3. We're going to start with this number that I just calculated. And now we're going to say, okay, well, how much of this would need to be, let me think about how to say this. Okay. So we're working backwards now, and I'm going to call that number 3. Sorry, it's getting all crunched together. Okay. So we're going to say if I have 1.22 times 10 to the 3 grams of ammonia, how much hydrogen did I need to have made that in the first place? Okay, think about that. So that's kind of like saying, if I want to make 10 ham and cheese sandwiches, how much ham would have I needed in the first place, right? So we're just doing, it's no different than that, right? Just think of this as cooking. If I want to make 17 ham and cheese sandwiches for Gordon Ramsay, how much cheese would I have needed in the first place? Okay, so that's what we're doing here, right? So 1.22 times 10 to the 3 grams of ammonia is the maximum I could make. So now we're just going to work backwards, folks. We're going to say grams of ammonia to moles of ammonia. Remember, don't forget the dimensional analysis process. Down, up, down, up, down, up. We know that that's 17.02 grams of ammonia in 1 mole. Okay. And then now I'm working backwards. I'm working from ammonia to hydrogen. Okay. So I need to have mole of NH3 here and mole of hydrogen here. And my balanced reaction tells me 2 moles of NH3 can be made from 3 moles of hydrogen. Okay, let's make sure that we're canceling units correctly. Okay, good. And then now finally I need to go moles of hydrogen to grams of hydrogen, because that's what we're trying to get to, right? We're trying to say what mass would be left over. And so we know 1 mole of hydrogen is 2.016 grams of hydrogen. Okay, so what do I get when I do that calculation? All right, so I can say 1.22 times 10 to the 3 equals, so that's that first number. I'm going to say times 1 times 3 times 2.016. So times 1 is the same number. So times 3 equals times 2.016 equals. And now I'm going to say divide by 17.02 equals. And then now I'm going to say divide by 2 equals. And yes, that's the number that I'm supposed to get. Okay. And so that's 216.7 something or other. 3 sig figs would make this 217. 217 grams of hydrogen. So what does that number mean? That number means if I wanted to make 1.22 times 10 to the 3 grams of ammonia, I only needed 217 grams of hydrogen. How much did I have in the first place? I had 5.00 times 10 to the 2. That's 500 with 3 sig figs. So I'm going to write that as 500 point grams of hydrogen. But now it's saying that I only needed 217. So what mass of which starting material would remain? Well, I'm just going to subtract it now. 217 grams minus 500 grams gives me 283 grams of H2 left over. Okay? So, and just again, to walk you through this in the simplest way, right? We could do the exact same thing here, right? If I had 12 slices of cheese, how many could I have made? If I had 6 buns, how many could I make? If I had 15 slices of ham, how many could I make? Okay? So from all of this, we learned that we could only make 5 slices of ham and cheese, right? So how much cheese would I have left over? Well, hopefully you can see pretty easily that's going to be 7. But how do I get that? Okay, well, I can work backwards and say, I know 5 ham and cheese sandwiches is made from just 1 slice of cheese, which tells me I need 5 slices of cheese. And if I had 12 slices of cheese up here, minus 5 slices of cheese, then I have 7 slices of cheese left over, right? So you can see with this simple algebra, you might think, or with these simple numbers, you might convince yourself you don't need to do this dimensional analysis stoichiometry thing because it just makes it confusing. Well, this dimensional analysis stoichiometry thing actually makes it a little bit easier. It helps you guide your way through, okay? So make sure that you're okay with doing a problem like this. We're going to get some practice doing a problem like this in lecture, okay? So I'm going to keep going with this, okay? And so we have another problem And this problem is pretty hefty. So I'm gonna skip going through this for now, but this is more practice for limiting reagents. Okay, more limiting reagent practice. So try this on your own, okay? Definitely you should try this on your own. The notes are going to be available for you to calculate this. But what I also wanted to show you, the additional problem with this is now this whole idea of percent yield. What is yield? Okay. So if I back up to this thing, and let me go to this, okay? So suppose I do this thing, right, with the 3 hams and the 1 cheese and the 1 bun, and it makes exactly 1 ham and cheese sandwich. 100% yield. That means I didn't waste any reagents, okay? That means everything was consumed perfectly and made exactly what I was expecting. This is still a 100% yield. I just had leftover ham and cheese, okay? But for example, if let's say in the process of making this, somebody took a bite out of this thing before we were making it, it would obviously no longer be like 100% yield because somebody consumed some of it, okay? So often in chemistry, we never get to 100% yield. So often, you never get 100%. There are side reactions. There are impurities. There are other factors that lead to reactions not giving you 100%. Okay? So what is this difference between actual yield and theoretical yield? Well, actual yield is what you made, what actually got made, and the theoretical is what you calculated should be made. What you calculated. So all of this stuff that we've done up to now has only been theoretical yield. Okay? So for example, I'm just going to you read through the problem and you'll see that you can get a reaction set up, and that reaction looks like this. CO gas, 2 hydrogen gases, and that makes CH3OH liquid. And the way this problem goes is it says, well, if you had 68.5 kilograms of this, 68.5 kilograms of carbon monoxide, and 8.6 kilograms of hydrogen, how much of this could you make? Okay, so I'm not going to do this in this lecture, but you can follow those exact other 2 examples that we did. Okay, and I'll tell you the answer that you get. So I'll say this one is number 1 and this one's number 2. So from number 1, from the carbon monoxide, you get 7.84 times 10 to the 4th grams of methanol. And from the hydrogen, you get 6.83 times 10 to the 4th grams of methanol. So which one is the maximum? Which one's the most that we can make? It's the 6.83 times 10 to the 4th grams, right? That's the one, that's the most. The least is the most, okay? And this is what we would call our theoretical yield, okay? We calculated it. We didn't actually do the measurement. We calculated it. But then now look what this problem says. This problem says if 3.57 times 10 to the 4th grams of methanol is actually produced, actually being that key word, then what's the percent yield? Okay, well, actual over theoretical times 100. So it would be 3.57 times 10 to the fourth grams all over, let's see, oh, the theoretical, there it is, 6.83 times 10 to the fourth grams times, 100 to make it a percent. I get 52.3% yield. So let's do that here in the calculator, right? So I can say 3.57 e to the fourth equals divided by 6.83 e to the fourth equals, and then as soon as I say equals, it's going to spit out the answer. So that's 0.52269 something. Remember, times 100 to make it a percent. So 52.3% with 3 sig figs. Okay, folks? All right, so I know I said I'm going to do this all in one shot, but I think that's actually a pretty good amount for this lecture video. So I might call this one A and the next one B, maybe. I think that's a pretty good wrap for this. So basically what we did on this one was only doing this concept of limiting reagents. Okay, so it's a big concept. It's something that's really important, and so this is a big one that I want you to be able to do. Okay, and so I'll do another last short video on these last two. All right, I'll see you later, folks.